All right, everyone. Section 5.6 called related rates. Related rates is going to feel a lot like optimization problems. So I'm going to do the same thing I did with the optimization problems. I'm going to walk you through the guidelines first and then just do two examples. And then we'll do lots more problems as we go over problems in the book. Two is usually enough to kind of get you started. Related rates are going to feel a little different than optimization. So remember, optimization was trying to find a minimum or maximum of some function. Related rates are just relating rates. Just like I said, we got speeds of two or more different items, and then we have to relate them somehow. So the main difference in these problems is, remember, in optimization, you had to have one variable, and here you don't, because we're going to implicitly take derivatives with respect to time. So just kind of walk through these, and then I'll just do an example. So I'll go pretty quick. The first step, again, just like related or optimization, is just to figure it all out, draw a picture, find the unknowns, give things variables, sketch a picture, label it, blah, 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 blah. Then we try to find a formula. Here's the nice thing. The formulas will actually be a little bit easier in this one because you're not having to get one in terms of the other. You just write a general equation that relates all the variables. Typically, it's going to be Pythagorean theorem. It might be some trig functions because you might have some SOHCAHTOA, some right triangle stuff, but that's pretty typical. Once you do that and you have that equation, just like optimization, you're going to take the derivative. However, in the optimization problems, you took the derivative and then you tried to minimize or maximize it by setting it equal to 0. This time, we're going to think every one of my variables is related to time. It's related to time. It's related to time. So that means we're going to take the derivative implicitly because everything's going to be with respect to t. Once you see an example, I think that'll make sense. Then you're going to get a general equation that relates all of the rates. And then you just substitute everything you have and solve for whichever unknown rate you're trying to find. It's pretty common that people want to substitute too early. You want to put in variables too early. I'll show you what that means as we go through. So here's the first example. I'll just do two. I'll read it to you and then I'll bring it down the screen and we'll just go through it. The ladder, 20 foot long, leans against the wall of a vertical building. The bottom of the ladder slides away from the building horizontally at a rate of 2 feet per second. How fast is the ladder sliding down the building when the top of the ladder is 12 feet above the ground? I'm going to draw a little picture here. I'll go back and forth to that. Basically, we have a building. Here's my building. Is that all right? Don't make fun of my building. Sometimes I see really cool buildings. We got this ladder that's leaning against this building. Okay. The ladder is 20 feet long. Okay. The ladder starts to slide away from the building horizontally at a rate of 2 feet per second. So I'm just going to draw this. It starts to go this way at 2 feet per second. So notice as that ladder slides away from the wall, it's going to also go down the wall, right? So the question is, how fast is the ladder sliding down the building when the top of the ladder is 12 feet above the ground? So we're going to go down here. This is my question mark. When ladder is 12 feet. All right. So the first thing we're going to do is generalize everything and write an equation. All right. Anything that's changing in the problem, you need to give it a variable. If it's changing, it has a rate attached to it. So you have to give it a variable. If it's not changing, you don't have to give it a variable. So that 20 is not changing. So I'm going to leave that alone as 20. So anything that's not changing, I'm just going to call this X and call that Y. Like I said earlier, a lot of my equations are just going to be Pythagorean theorems. Boom, done. I got my equation. Simple. Now the related rates idea is a little bit trickier. So remember, each one of these has X and Y are related to time. So I could write them as some function of time. So when I take the derivative, I'm going to go 2x, but then it's like implicit differentiation. Remember that x is some function of time, some function of t. So then I have to multiply it by its derivative. In implicit, we would have called it x prime or y prime or z prime, whatever, but I'm going to call it, it's a rate, so I want to call it a rate. I'm going to call it dx dt. So I think about it as the rate of change of x with respect to time. How fast is x moving? In this case, we know what that number is. It's 2. But I'm just going to leave it like there and keep working on this. So same thing on y, 2y dy dt. So take the derivative implicitly. Remember, every time, no matter what the variable is, x, y, z, r, t, whatever you call it, theta, when you take that derivative, then you have to do a chain rule. And the derivative of 20 squared is 0. So now notice I have 1, 2, 3, 4 different variables in this problem. I'm looking for one of them. So typically in the problems, but not always, but typically we know all the variables except one. Sometimes we have to relate them. It's kind of unusual, but sometimes we do. So notice the question is, how fast is the ladder sliding down the wall? That's my dy dt, right? That's variable 4. That's the one I'm solving for, which means I should know all the other ones. So now is time where I can start plugging things in. Remember, I made this comment here, don't plug things in too early. Sometimes people want to put this 12 in really early, but remember that 12 is changing. So I can't put that 12 in until I take the derivative, and then I can go back and plug it in if I need to. So that x is, whoops, sorry, the ladder is 12 feet, so that's the wrong place for the 12. The 12 is actually here, right? And there, that's 20. I can find the other one by using the same Pythagorean theorem. I think it's a 3, 4, 5 right triangle, actually, which is 16. And now I can start plugging in. So it's 2 times x. X is 16 times dx dt, which is 2. Plus 2 times y, which is 12, times dy dt, which is what I'm looking for, equals 0. It's just an algebra equation to solve now. What do we got? For 64 plus 24 dy dt equals 0. So I believe dy dt equals 24 over negative 24 over 64. You can go ahead again on these. Just go ahead and use a calculator. You can put them in decimal form just to simplify. You can leave it like this. Calculators are fine to use in these problems, just to computational things only. And I think we're in feet per second. So let me do a little reducing, I guess. What does 4 go into this? 6/16, so 3/8. Negative 3/8 feet per second. Why negative? Negative. Some people want to say it's negative because it's going down. It's not actually negative because it's going down, believe it or not. And we'll see this in another example. It's negative because the distance is getting smaller. Seems like the same thing, but it's not exactly the same thing. It's negative because it's getting smaller. All right, let's do one more example. 1 o'clock, ship A is 25 miles south of ship B. Ship A is sailing west at 16 miles per hour. Ship B is sailing south at 20 miles per hour. Find the rate at which the distance between the ships is changing. All right, so let me draw a little picture here. Oops. I'm going to jump back and forth, sorry. 1 o'clock, ship A is 25 miles south of ship B. So we'll call this A. We'll call this ship B right now 25 miles. It's 1 o'clock. Then ship A is sailing west at 16 miles per hour. Ship A is going this way at 16 miles per hour. Ship B is sailing south at 20 miles per hour. Change the color on this one here. Ship B is sailing this way at 20 miles per hour. And then notice the question is, find the rate at which the distance between the ships is changing at 1:30. So I'll write that down. Rate, distance changing at 1:30. All right. So what I'm going to do, I do this, I take what's called a snapshot picture. These ships are moving. So I just let them move for a little bit and then I stop them. So at some point, I stop them. Don't worry about the scale of the picture or anything. It doesn't really matter. A went for a while, B went for a while. There's the distance. Picture that purple line is moving, right? As B moves, as A moves, it's moving. Okay? So now what we want to do is throw in some variables. So I'm going to call, got to be a little bit careful here. So I'm going to call this. So think about this. Now I have this little triangle that's been formed, right? And then there's this little previous distance up here also, right? So this whole distance was 25. I'm going to call this X. All right. I'm going to call this Z. Okay. And I'm going to call, now you have a choice on what you call Y, actually. I'm going to go ahead and call this Y, I guess. I just have to be a little bit careful. Some people want to call this Y, which is okay also, because that's going to be important in a second. If I call, whichever one I call Y, the other one's going to be 25 minus Y. I'm going to do it this way. I don't know if it's the easiest way or not. The other way might be a little bit easier, but they're roughly the same. I like my equation this way better because my equation is just x squared plus y squared equals z squared. Again, a little right triangle. So now I take the derivatives. It's 2x dx dt plus 2y dy dt equals 2z dz dt. Don't forget that implicit stuff entering the rates. Notice I haven't put any numbers where they are, anything like that yet. Okay. So now I got six variables. Yeah, six variables. So I'm looking for one of them, which I think is dz dt, right? So now I have this snapshot. Now we've stopped moving. So remember, it's at 1:30, so half an hour later. So here's where I can now find x, y, and z and plug them in. Do not plug them in before you take the derivative because they're changing. So half an hour later, I think x, this guy's going 16 miles per hour. So that's an 8. Y is going 25 miles per hour. So after half an hour, 20 miles per hour. So after half an hour, he's gone 10. But be careful here. This is the 10, right? So that means he's gone, this is 15 right there. And by the way, in case you didn't know this is an 8, 15, 17 right triangle. All right. So now here's the last step. By the way, I'm just going to cancel out these 2's if that's okay. So now I get x, which is 8, times dx dt. Now there's always an issue on dx dt. Some people say, should it be positive or should it be negative? I'm going to pause for a second. Should dx dt, the rate, be positive or negative? It is a 16, right? Should it be positive or negative? Most people want to say it's negative because it's going to the left. Fair enough. That's what we've always done in our life before, right? Negative is left is negative, right is positive, right? However, think about the logic of this problem, that if this boat went to the right or to the left, east or west, would the answer to this question change? I'm going to pause for a second, ask it again. If this thing went to the right or went east instead of west, would the answer change? And you should say no, because it's the same picture. I could have drawn it the other way, you wouldn't even have known. So I'm going to make that rate positive, and it's positive not because it's moving right or left. This is where this becomes really important. It's positive because it's getting bigger, simply because it's getting bigger. The up, down, left, right is not positive, negative in our world right now. All along in our world, up, down, left, right's been positive, negative. Now it's bigger, smaller. So when I get to my y, which is 15, my dy dt, that rate is 20, but that's actually a negative rate. Not because it's going down, but because y is getting smaller, okay? My z is 17. My dz dt is what we're looking for. Just a matter of taking out my calculator now. 8 times 16 plus 15 times negative 20 divided by 17. I got 10.12 miles per hour, I guess. It did turn out to be negative, just so you know. And again, it's not negative because of direction. It's just negative because that distance is getting smaller. So that blue line is getting smaller at this point. But the rate at which they're changing is 10.12. So those are two pretty good examples. I know this is going to be hard the first time you see it. Do the best you can. I'm just going to do more and more problems. Actually, on Wednesday in class, on your Wednesday day, the asynchronous day, I'm going to send you some more solutions to these. You can see some more problems. And then we'll go over more on Thursday. So good luck with these.